Today we're talking about Master Key Masonry Design. Master Key Masonry Design is one of our standalone programs. So what I'm going to do is I'm just going to jump through these little quick slides as part of introduction. So we have like 4 different bundles to be the big building design suite for doing your multi-story buildings. We then have the Power Pad Plus for doing your smaller work, sole practitioners, or even in a multiple user office for having a small and a big together, and then the specialist portal frames. But if none of those suit you, then you can go through the custom suite of programs. So I just click on custom, and here we go. We can do frames, we can do portals and simple steel beams. We have wind analysis, full bin integration, finite elements and dynamic analysis. You even have, if you can catch it here, the seismic analysis as well. You also integrate that in with steel, concrete, composite connections and timber design. And then finally you have the standalone modules for masonry, retaining walls and pile caps. Although pile caps technically is also an integrated design these days. I'm just going to go straight into the masonry on its own. So I'm just going to close this down. Back into my home screen. So I'm going to start MasterSeries 2020, and it's the 5th of October edition, 2 days ago. Little patch update released, and I am going to log in to the cloud as a MasterSeries user. So what we've got is our frames and our portals and everything, but what we're interested in is the standalone straight away in masonry design. So here's some projects I've done before, and I'm just going to come in and take this one, wall, and we'll see it gives you a nice pretty picture of what we were doing previously. And you can store your data files anywhere and they're fully associated. So open the file, and I come to this pretty horrendous looking wall. 3 openings, a wind post. We've even got a pier at the end to help strengthen it, and we've got some point loads on the top. Now, we quick review. Anybody who's used the MasterSeries knows that this program got a total makeover this year. A new interface with easier to access and use flexibility in the software. And we are looking at a reinforced 2-way spanning vertically and laterally loaded stiffened cavity wall with a wind post to EN 1996 Part 1 2005. The screen's blue. Why is it blue? Well, a couple of reasons. One is we need to solve this because we do a finite element analysis, a yield line analysis on this wall. We need to just not go crazy with auto design all the time, particularly when it's complicated like this. So if I do analyze, off it goes, and it's going to do the analysis in several seconds. Here we go. 4 or 5 seconds, and we've now got our analysis, and we're seeing the results. We can see, if I zoom up, that we've got a utilization of 73%, so 25% reserve on that wall. But let's not go through all of this initially. Let's just start a brand new brief. Let's take it from scratch. Let's add a brand new brief. We're going to call it Demo 1 and create the brief. So we can have multiple sets of results in the one data file. So here we go, very simple, and it doesn't know much at all. First thing I'm going to do is I'm going to say, yeah, auto solve. I'm going to keep it simple. Let's do some auto solving. The next thing I'm going to look at is general. It's going to be, we'll keep it per pen fill. It'll just be the main wall, and it'll not be a faced wall, and the live load won't be storage, so we don't need to alter our load factors because of that. All very simple. The analysis doesn't tell us much, but we're going to go for a medium analysis. We'll see what that means in a couple of minutes. So coming up to the wall setup. So we're working from left to right, and we're going to go for a 5 meter wall, and consider 5 meters by 3.25 wide, and it will be 100 inner block work and 102 outer in the UK clay brick or concrete brick. And we'll not stiffen it. We'll have no piers or anything at the minute. We're going to keep this simple, and we will not make it a masonry column. So just close that. So now we have a wall, and we've got these default fixities. So if you look at your codes in the simple tables, you'll see that the double hatch, the crisscross hatching is fixed, and the single hatching is pinned. Very straightforward. So we'll go and set those up. So I'm going to say that the left is also fully fixed. And I could turn around and say that the right is free. So we have nothing on the right hand side, but I'm going to keep it simple initially and make it pinned. So pinned, pinned, fixed, fixed. And as the code recommends, we just treat the two walls to be the same. If you have a pinned and a fixed leaf, you would consider it to be fixed unless the pinned leaf was thicker than the fixed leaf, because everything has to follow through in its profile and everything due to all the ties. So I'm very happy. Close that. Now we're still setting it up. Rather than going to masonry units, I'm going to go straight to out of plane loading, and we're going to choose our basic loads. Our WX is going to be 1 kilonewton per meter square. Is it non-critical? If it is, we can reduce the material factor, and we don't need to worry about that because we're doing a yield line analysis. So if it's non-critical in the UK, you can reduce the load factors. Personally, I don't believe you should do that, because I think for the person standing behind the wall taking shelter, it's most definitely critical. If it's on the third floor of a building, it's most definitely critical. Falling out may not cause the structure to collapse, but it could do damage to whoever or whatever is underneath. So use that non-critical function with caution. I'm going to put no additional loads on and just close that down. So now we've got some walls, and if I analyze it, we haven't defined any mortar or materials that are sensible. So inner leaf concrete blocks, and we're going to say category 1, class 1, and we're going to say unit strength 7.3 standard concrete blocks, and it'll come through and do some calculations for us. As you can see, as I've suddenly changed that, it's done all the design for us because we're in auto solve. Outer leaf, I'm going to go for clay bricks, and I'm going to go for water absorption in the middle. They're not real specials. And I'm going to go for 10 Newton standard clay bricks. If I want to, I can override the default values for both flexural and axial. I think that's axial, that's flexural. Strength of the masonry blocks from test results. But usually in the UK we normally stick with the standard values, but you have the option. Very straightforward, very easy. So we've done our first design. It works. I know it works because it says in here 0.937, so just under unity. This wall works very, very well. It's really optimized. Secondly, we can see down here that we have a white screen. So if I was to go back to the edge fixity and make the left pinned as well, you will see it's 0.096 overstressed, so it's nearly 10% overstressed with this being pinned and pinned with only fixity in the bottom. Naturally, the fixity at the bottom is probably one of the ones that have most debate. It depends on whether you use an engineering brick to model a DPC, or you're on the third floor anyway and it is continuous, or you're using some sort of force transmitting DPC. So if you want to play safe, you make that pinned. But at the minute, it's not working. We've got several choices, and one of them is to go and increase the strength of the blocks. If I just pull this over here, and I'm still on auto solve, and I change the 10.4s, it's having a think. And here we go, it's got virtually no change in difference. And if I change my bricks to 15 Newton, again we should see there's very little or no change in strength, because it's really the flexural strength that doesn't change. The strength of the blocks and bricks is more to do with the axial, certainly for the clay bricks. So put that back to 10. You can get some gain by going up to say 17 Newton blocks, but it'll be small change in its change in value. Yeah, so there's a 5% improvement, but we're still failing. So let's go back to the more economical 10 Newton blocks, and we'll just close that. We could change our execution class for construction or manufacturing. We could go for a higher manufacturing class and see if that gives us a improvement, and in this case it's not really doing anything for us, so I'll just close that. So what's the other option? Other options in this case is very simple. We either thicken the wall or we put some more resistance into the wall. So thickening it is dead easy. That's just part of the wall setup. We change the inner leaf to and make this a 140 inner leaf. And here we go, we've now got a white background. So that would solve that problem, but who wants a 140 leaf wall? The architect is selling it per square meter or square foot, and the client, so we really don't want to suddenly lose all that area of retail or housing space because it costs money. So the only other solution is to start and reinforce this. We can reinforce our wall in one of two ways, or in both ways in fact. So simplest way was to come along and slip in a wind post, and I'm going to choose a wind post at the midpoint, 2.5 meters along, and I'm going to add in a, definitely not a UC, probably a square hollow section, and I would come all the way down to something nice and light like a 70 by 70 by 5. I like to keep the 5 and above millimeters thickness for durability, and it will be 355 grade, the default grade these days for hollow sections, although it may be that you want to use the 235, the cheaper European section grade, just to make sure. Now we've got several things we can play around with this. We can say that it is fixed rather than pinned at base, and fixed rather than pinned at the top. We could also make it free at the top. If it was a freestanding wall, we can put these posts in, make it fixed at the base and pinned at the top. The other thing we're able to do is to say that we want to break the continuity. So we're going to break the inner leaf continuity. That changes the whole U-line patterns because only one of the two leaves is continuous now. And what that's telling me is that we're going to embed this into the wall. Now, in reality, when you embed in the wall, most fixing methods are deemed to be fixed. It's only when you start to put flex cell, around the hollow section with your ties that you can get this flexing of the wall, and therefore it's not fixed. So playing safe is to break it, and I'm just going to close. And we can see now we've gone from 1 all the way down to 0.5. It's really, really, really strengthened it. But what we're seeing here is the U-line pattern. And the U-line pattern is still running straight through the wind post. That means in this area we're still flexing top to bottom. It's going from here spanning to here, which means it's just using the wind post as a strengthening of the overall member. If I go back and change this wind post, even stick it up to the more common 353 and apply and close, you see it's still, and it's got a better capacity. Let's go and put in a heavier 100 wind post. It's 100 by 100 by 6.3, very popular size. And now we see a difference in the way the U-line works. The wind post itself will not actually yield, because that's all we're doing. We're looking at this wind post enhancing the overall strength, because we're not designing the wind post as a separate component. We're designing it as glued onto the wall in whatever fashion and enhancing it. So in this case, the post is so strong that the flexing is flexing across in this direction. So it's going from here, here, and the big yield line down there. So those are the two different ways that we can handle the wind post. Now, wind posts, they're great. We've been using them for a long time, but they're problematic because, okay, they can create cold bridging, possibly not that much if it's in the inner leaf. Also, it interrupts the construction process, bringing in a different trade, putting in holding down bolts. It also makes it a less neat construction. A nicer way to design your wall, to take this and delete it and close. And now we've got no wind post, we've got that failure we had before, but instead we could put a pier. Again, horrible solution. So if we went back to the wall setup, we could say we want it stiffened. If I move over here, actually what I'm going to do first of all, I'm going to take this and I'm going to turn off the auto solve so that we control it better. Go to the wall setup and I'm going to ask for a stiffen wall. I'm not going to ask for repeats. I am just going to put one wall at 225 in and starting 225 in the center, and we'll put the first one at 500 and there. So let me move away. Single wall 225, or in fact 250, 2500. Tommy fingers. And now we have this centered wall, which is a 215 by 440, and that will strengthen it. Easier to construct, not pretty. And if we then do an analysis, we will see that it has given us some strengthening of our wall, which is down to 0.98. 0.98 works, but why is it not giving us a white background on the left hand side? That's because we're using a yield line analysis, and our yield line analysis we've chosen is the medium density. And if you look down below, it's telling us that we need, so it's posters are being ignored, that's fine, but it's telling us to consider the density. So we need to check it to a higher density, just in case that higher density gives us a failure. Now, if I just try and get rid of this wind post, there we go. Don't have a wind post at all. It was just been ignored, but now it's solving. Now, let's get to our density, and let's choose a fine density. Once we move to fine or super fine, we automatically turn off auto solve because it is not practical. Even on big i7, i9 processors, it still takes a second or two. You can see in the fine, we're going to count the seconds here up to maybe 30 seconds because we've got a very fine mesh, and if you double your mesh density, you quadruple the, double the density, you have 4 times the amount of work to do. And then that can be factored because of the number of permutations is increased by that. It's a bit like 6 balls or 7 balls in your national lottery. So here we go. We have increased it to fine, and it's gone from 9.7 to 9.95, so 0.5%. So you might ask yourself, oops, sorry, I clicked on that by mistake, and I apologize. Just while it's doing its little thing, people are asking, can you use a proprietary wind post? Yes, you are able in the wind posts to input your own name and moment capacity of the post, because really that's what we're really after, is the moment capacity. So if I was to go and change this down to super fine, it would take 2 or 3 minutes to solve because it's really, really fine. And we know already it's going to fail. So back to medium density, which will happen in milliseconds. We know that we're within the cusp of 2%. So what we're going to do is we come back to our wall setting and we're going to increase this from 215 to 325. I'm going to stick a bigger wall in for the pier, and it's now made that down to 80% utilized. So has its advantages, but nowadays you don't need to do that. So let's take out our stiffening. Just say okay, close that. And we'll come to the other way of reinforcing the strength of a wall, and the clue is in the word reinforcing. We're going to add in bed reinforcement. So we can enhance the lateral strength of a wall, and some of the codes will tell you that you shouldn't go above 50% unless you're happy with cracking. So we're going to accept that. So sensible is inner reinforcement, because outer reinforcement is going to cause us to watch our covers. Now I can just turn off the auto solve here a second, just come here, turn off that. As you can see, it can get a wee bit pernickety as you're editing and changing these. So we can put in a user defined bar size and spacing and how often you want them. 75 mil vertical, which means it's every brick course, or 150, which is every other brick course, which is a more common, and strength. But if we go to the library, we can turn around and choose the Beckhart, the Ancon, the Apollo. I am going to go for my favorite, which is the Muir 4 compact reinforcement on a roll, and it's going to be A for internal, and it's on 100 walls, so it'll be 50. And I'm just going to close that down and ask it to analyze. So off it goes, and it's just doing the calculations now with the bed reinforcement in this wall, and you'll see that bed reinforcement has dropped me right the way down to 70% utilized, well within tolerances. Now we could probably jump back and try 225, save a bit of reinforcement. One of the nice things about the Beckhart Muir 4 compact is it comes on a roll. The roll is 30 meters long. It's got 7 strands, which are tiny, and the yield stress is scary, 1700 Newton. It also is able you're able to cut it with a pair of shearing scissors. So you roll it out, cut, roll it out, cut. So you've very little lapping to do that you have with these older style rigid 3 and 5 mil bars, which are common in default. I think it's 1.8 meter length, and you have to lap them and everything, or 2.4 meter lengths. The Beckhart's 30 meters, and you cut. So 30 meters, you're going to get 6 of these runs, and then another 6, and then another 6 as you need. So there's virtually no wastage. Also, you can store them somewhere secure because it comes in a roll, and you don't lose it from sight. So that's a great product and a great addition to the software, this Beckhart bed reinforcement. If you see, you have, looking at it, the internal and the external, and then you have the special. The external, as you can see, is only going to have 30 mil between the bars, so there's not going to be a lot of bars because it needs that extra cover. And then there's the newer 80 mil internal, because it's saying, well, we're internal, we don't need cover, and that's going to really strengthen you up. I didn't realize they'd produced another product in the range, and see what that does. Just analyze, and that's going to bring us back up to an even stronger wall. It's saying actually the wall's too thick, so the covers, so it's actually looking after you all the time and saying no, 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 and therefore your unity. So go back out to rebar, back to the more standard 50. Everything's happy, and we're done. So that's your basic laterally loaded wall. Now what we want to come to is the stuff that you can't really design using the tables, although the bed reinforcement and the piers will be some job doing that all by hand. And that is when we come along and look at our other options. So we can go and we can try wall loads, vertical loads in the wall. Somebody asked about doing loading on wall. Now these are kilonewtons per meter run. So I'm going to say, coming from the first floor, we have 7 kilonewtons on the inner leaf, and we have a 3 kilonewton live load coming from above. And on this floor we have again another 5 and 3, so 1.5 by 2 meters wide and 20 mil eccentricity. Probably increase that one to about 15 because it's going to have wall as well as dead loads. So EC not, we can ask it to be leading or accompanying, so we can ask the QK to be leading and accompanying, and we can flick those around if we want to. Outer leaf, you could turn around and say, well, you have a dead load of 7 and that's it from self weight from the upper lift, and we'll close that. So now we analyze, and we've got these loads, and this analysis gives us some interesting concepts. It's actually strengthened the wall. The loading from above has strengthened the wall because it is pre-compressing our wall without causing any damage. So maybe we could get rid of our rebar. So let's just drop off the rebar for a second, come back here, analyze, and see what happens. And we're at the 72%. So having that pre-compression from the upper levels will allow us to make the wall work. Now you might argue if this is going to be 2 lifts that should be continuous. I'll leave it as pinned just to make my wall work a bit harder. The next thing I want to introduce is some point loads. So I'm now going to add in a distinct point load, and it's going to be 15 kilonewtons dead and 5 live, and it's going to start at 1.75 out. And now we're going to ask for the B length and width. B not for breadth, but B for bearing. Bearing length and bearing width. So the bearing length is the width of the beam, so we're going to say it's a 125, so 125, and the bearing width, it's got to be at least half of the section, so I'm going to say 50 mil, and coming in and close. So now we analyze. It's going to do the yield analysis with the point load and the line loads and the lateral loads, so a triple loaded wall, and we will see that our bearing is a problem. So let's just jump straight back in again. Well, we can put a concrete pad in, so make it 440 by 250, or I'm quite inclined to make it 215 by 75 engineering brick, see how that goes, and analyze. And in our case, an engineering brick or 2 engineering bricks is easier to put in than casting in a wee bearing pad. So that's a single point load. We can put another one in. So that's our point loads. Now, out of plane is our wind loading, and if you remember, we can actually put on a triangular load on the wall, and that's because sometimes some of our clients like to use this for little grain stores and things like that, or even the basis of a retaining wall type structure that's just cast onto a foundation. So they want to apply a retaining triangular load. Edge loads, we can put edge loads around the top, bottom, left and right, and I didn't actually know we could do that. I apologize. The edge fixity must be free. Right, that's really to do with when we get into openings and we subdivide walls. Using the old methods, you were able to subdivide a wall into sub-panels and then put edge loads around those. Otherwise, why would you put an edge load? Because it's supported. So you can only put an edge load where there's no support. Kind of makes sense. Line loads, now that's just your good old-fashioned line loads. So if we were to put some sort of racking along here, or we had a floor that was coming in that had some sort of lateral force on it, we could come along and say, I want a 1 kilonewton load to be applied between 1 meter and 4 meters, and we'll put it from, it's 3.5 high, we'll put it at 2.5 up and 2.5. So now we've got this horizontal lateral load pushing onto the wall. If you're doing freestanding walls, that might be useful for barriers in crowd control. If it's a small freestanding wall in a car park or a walkway or whatever. You can also turn around and use this with a wee bit of lateral thinking. If you said, well, actually, I want to apply a 2.5 kilonewton point load onto the wall, what you'd do is you'd say, let's make it 25 kilonewtons, and then let's make it span from 2 meters to 2.1 meters, so 100 millimeters. So you'll find that that 25 kilonewtons will equate back down to 2.5 kilonewtons in that localized area. And it's very, very useful. I am going to take that and just delete that line load. I'm happy with everything else. So a wee bit of fun and games with loads. Finally, where we want to go to is openings. And this is where the yield line analysis really, really shines. Openings. Okay, let's put our first opening at 1 meter in, 0 height, 1.2 wide, and it's going to be 2 meters high. And we can tell it to span 2 ways, or we could say vertically, weird, horizontally, maybe a roller shutter, or bottom free, which is the door. And when we move away, there it's applied. I'm going to put a second opening in at 3 meters along, and it's going to be at a height of 1.2 meters up. And it's going to be a meter wide just, and it's going to be a height of 7.75. And it will be the default 2-way spanning. And there's our door, but of course we're not far enough away. 2 meters is already encroaching that. That should have been 3 meters. That will still analyze and work with that combination of openings. It's something that people do sometimes for weird architectural reasons, but in my case, I do prefer them to be separated. So there we go, and we can now say, go on, off you go. Complex analysis required, and it's giving us the yield line, and the yield line is telling us that it doesn't work. So we're back in a full circle, very complicated wall, but this time we have openings and point loads on it. So we've got the choice, do we add in the wind post again, or do we add in the bed reinforcement? I know which I'm going to go for, the bed reinforcement. Let's pop in some bed reinforcement, and we're going to put it every 225, every third course, and close that, and see how we go. Analyze. Having a think, and it's going to give us, yep, it's worked. So every third course bit of bed reinforcement is going to strengthen, particularly this huge big flexural area coming back in here, and you can see how it's working now. Colors. Why have we got 2 colors of yield lines? Well, if you think of slabs, if you think of beams, sagging moments is what I would call them, sagging yield lines, and these are the hugging ones. So from this fixity, you're getting a fixity, fixity, and then fixity around here. You'll also notice the fixities don't go to the edges because it's looking at the lower bound solution, and we're finding that a weaker solution is when the yield line comes across here and it sort of cracks here. So there you go, that's your solution. And the finer I make my analysis, the more micro yield lines that will occur and appear, because it just is sort of like crack, crack. The same way, you know, slabs will not just crack in one position, they will crack and then another one will come in the secondary to it, provided it's still going plastic. So we can see this yield line. Now the second thing is, why are some of them very thin and some of them very thick? The thickness is to do with the degree of rotation, to do with the degree of moment, plasticity around that. So once it cracks, it's got its plastic moment, but the thicker ones have rotated more, so they're the more dominant ones, as you would expect. And hard to see, but there is a yield line, not here but from here all the way to here. Yes, there it is from there to there, as you'd expect, with a little bit cracking across to there. So very clever, very powerful design of masonry walls. The last thing I want to look at is the good old-fashioned freestanding wall, and I'm just going to come out and pull this one in here. So what have we got? We've got a wall that's embedded somehow, fully fixed. It's a single skin wall. It's got a 5 kilonewton line load on it, and it shouldn't really have a point load. Doesn't make sense. Let's get rid of that point load. Delete and close. So single wall. Let's recompute, see how it goes, and we will see that this wall with a 5 kilonewton line load across it from some sort of surge or whatever, 1200 up, is actually working. Now we have introduced a wind post. That wind post will have to be fixed at base, free at top. If I was to take it out altogether, then you might have some problems in your wall. So we can do freestanding. Now if I wanted to do a freestanding, let's get rid of the line load. Where are we going? Wall loads, point loads are out of plane. Line loads, and let's just delete that altogether. Delete the whole thing. There we go. Basic load, we're going to have a wind load of 1 kilonewton, and it's freestanding, so we'll make it non-critical, and we won't worry about that ratio. I can now get rid of my wind post because I do not want wind posts in these freestanding walls. Delete. As you can see, the user-defined ones allows to give us a description and a capacity of those for you. Now I need to get rid of these two fixities at the ends. Left is free, right is free, fully fixed bottom. That's all we have. And when we analyze, we will probably find that our utilization is not enough because these 215 walls aren't enough. Now we're 60% overstressed here. Bed reinforcement is going to be as much use as a chocolate teapot or an ashtray in a motorbike because it's flexing in the wrong direction. What we can do is we can introduce piers, or we can thicken it. We can also, to a very limited extent, play with the masonry strength. It's concrete class 2 blocks and it's 10 newton blocks. So if we look at what our current ratio is, it's 0.1638. If I go all the way up to 17 newton, it's probably then going to recompute down slightly different, but very little. Nope, it's not giving no strength. We're already hit that cusp of any more, and there's no more flexural strength. So we need more material or something else in resistance, and my solution to that is wall setup. Let's go for stiffened, and let's go for piers, and we're going to go for piers at 1800 centers. And I am going to go for, well, 215. On a 215 isn't much cop, so that's going to be 440 as well. So 440 by 440 outstands. And we're going for these at 1800 centers. And I'm just going to close down, reanalyze, and see how that goes. And we're just there. We're nearly there, 3% overstressing. A wee bit less than the wind load, or maybe a wee bit of increased depth in our piers. But as you can see, they're not happy bunnies. They are not happy. My solution here would be to pull these closer together, but that's still a chunky wall. It would probably be a lot simpler to make it slightly thicker, because you only really get this enhancement around a certain width of the wall. So I am going to come to wall setup. I'm going to change that from a 215 to 325, take out the stiffening, see what happens. and it's now working. So it's simpler to construct and looks nicer for the client. And the other question you could ask yourself is, well, how high can this wall go? Would we get away with a 1800 wall? No. Sorry, auto size. We're changing small things, we can do that. And no, we're just so close to failing. Although, and honestly, it's not going to affect this. The yield line is clear. Going to a finer density will not have a problem. If I take this down to a finer density, it's going to give me exactly the same value because it is just a cantilever wall and nothing else. And you can see very quickly it comes to the same conclusion and says, well, that's spot on. So we could make this 325 wall 1800 high. So I'm just going to have a wee quick look at questions. This here is the advanced U-line analysis methods. And there are two versions of this program. There's the full version, or there's the version that comes with PowerPad. PowerPad doesn't have your bed reinforcement. Openings, you can have two openings, but they will only use the simplified methods. So if I went back to the previous wall and I went to turn off this, it's going to be unhappy because you can't have three openings. You only have two openings with that sub-panel method. Likewise, we can't have wind posts if we're using PowerPad version, although you can upgrade your PowerPad versions. Anybody who uses our PowerPad software, you get the simplified version of the Masonry. You can upgrade to the full version for about roughly a 30% discount on the full cost. What concept do you consider for your wind post? A support or a stiffener? It increases the stiffness of the whole structure. So it's still going to move, and it is obviously it's a U-line analysis anyway, but it is improving the moment capacity of these blocks as you go down through it. How is base fixity achieved in practice, David? That is one of those eternal questions for structural engineers, and I could turn around and say it's not for us to say. We give you the tool to add in fixity or not. Certainly if you're using this in a multi-story configuration and you have continuity between floors, then it will be fixed. The other popular solution, a little more expensive, is to use an engineering brick for the first couple of courses, and your 20-30 Newton engineering brick is going to stop the moisture ingress, which is what you're really after, and not have a DPC. Thirdly, there are proprietary DPCs that say that they will give continuity across the DPC. So now, talking about supports, one thing I never covered is if you look at the edge fixities and you think about, say, for example, this one, say it was shot fired into another wall, into a concrete column, rather than being into another wall that's continuing across or turning through 90 degrees. And you weren't happy with assuming full fixity, although most times you should be. Then you have the option of saying, no, I want to go partially fixed. So if you were saying you want it to be fully fixed, that's 100% fixity. If you put 0 in, that actually turns around and makes it pinned. And if you put in minus 100%, that's free. So you have a range here of plus 100 to minus 100. And that's all to do with the formulas in the background that are used to simulate the fixity of the walls. So I would never argue that you should allow it to be 80% fixity, because I don't think it's a good call. You know, if it's not 100% fixity, it's got to be reasonably less than fully fixed, because otherwise, what? How are you getting that? So, you know, certainly 50% or 25% is a doable solution. Now if you have something that's jammed up against something else and you can argue, well, it would give about 10% fixity, then that is going to give you again a degree of fixity, so 10%. So that is the partial fixity is a useful tool in certain instances to make a wall work. You have to be able to stand by that yourself. When you add the dead and live loads vertically, should this be factored or does the software factor the loads? Everything is working loads. Everything is then factored by the software because your GK and your QK are obviously different load factors. Yeah, there we go, which is really important. You know, if you have 2 or 3 different loads, can you apply one as being for the QKs, not the G, not the dead loads as we would call them, but for the live loads, the transient loads, what's leading and what's accompanying, you can then play around with that. And the software will mix and match that until it finds the worst combination. So yes, it's very, very smart in that. And it will actually look at different permutations if it has to on that. Naturally, from normal dead and live, you don't have that problem, but when you have dead, live, and wind, particularly in horizontal loading and things like that, you know, you really want to consider that they're not all being applied at the same time with the same load factor, and it will do all that for you. Carla, does the software check the wind post or are further design checks needed? The wind post is inherently absorbed by the wall, and its properties are absorbed by the wall and strengthen the wall. So there's no additional design really required on the wind post because we're just taking its properties to strengthen the overall wall and see whether or not yield lines occur. When the yield line occurred, if you remember, and I go analyze, when the yield line occurs vertically down the edge of the post, then the post is not yielding but resisting the wall. But again, its contribution has already been taken care of in the analysis, so you don't need a second set of design on it. When the yield line is going straight through the wind post, perpendicular to it, then that post has gone plastic, and that's a yield line with that post having yield at that point. But that doesn't mean it's failed. That just means that it's all part of the overall ultimate limit state yield line. That is the weakest, and then you obviously back calculate what your load factor reserve is. So an interesting concept. Can you deal with hollow block walls? That's a very good question, and it's something that's come through with the Eurocode. If we were designing to BS and we went to a masonry unit, we would see we can have it solid or hollow filled. So I'm going to say hollow filled. If I was to come back out and change my design to Eurocode, at which point it suddenly got annoyed, you go to Unit Masonry. That doesn't exist because you actually give it hollow blocks have their own reduced strength and normalized mean compressive strength. So be careful in the Eurocode you're using that normalized mean compressive strength as if it's the solid wall. I actually prefer the British approach, that it is different and should be taken differently, rather than just saying, oh well, we've lost half the area, so our axial is twice or a half the capacity, and our flexural is 3/4 because it's on the outside that we got the material anyway. So yeah, it's doable in the program. Do you need to change the densities? The densities seem to be 239. Good question. The density of block walls changes and varies considerably. A with strength and B with composition. So yes, you can go in and change these values to be what you want. The density is only used to improve the flexural strength. Only used is most significantly used to improve the flexural strength of the wall in the x-axis. So yes, watch your densities is the simple answer there. Would it be possible to put a stepped retaining wall? Stepped wall for step freestanding wall? Not really. Although you can certainly design the top portion for that. If I went to my wall, here's how I would do it. If I want to do an 1800 high wall, but I didn't want to do it 325 over the full height, I would first of all design the 1800 for the 325, and then if I wanted at 900 up to drop that down to 215, I would then do a second wall that is only 900 high and justify that for the portion. So up you come. There will be a slight variation in the overall strength and density of the wall, and maybe you should consider reducing your density by that lost ratio of material. But other than that, it's not going to be any good. How would you consider reactions from lintels or other openings on a 4 meter wide opening? Well, when we're dealing with our openings, we say how the opening spans, and I think that's important, because if you're making this wide, you might say no, it only spans horizontally, or it spans on all three, because if it only spans on all three, that's significant. And roller shutter door, it's most definitely all three at the maximum, possibly only the two sides, because when it's closed, it's pushing onto those two rails that are the two sides. So that's how I would transfer the load. Now, interestingly, you also have the option of coming along and, believe it or not, saying no load. This is an opening that exists as an opening. Doesn't have a door, doesn't have a window, it's an opening, an archway or whatever. And you can let it work without any additional loading on it. And that's also significant. Is an external wall return with adequate return length a fixed edge for the main wall? Gregory, you've answered your own question, because if it has an adequate return length, as defined in the codes of practice, then yes, it is fixed. If it doesn't, it's simply supported. Remember, the software is a tool to using your design and making things faster for you. Okay, I think that's about it. So it seems to be the two things that people who use the software want to have more of is gable ends and localized reinforcement. So certainly we've made a note of that, and we thank you all for coming along and viewing the software. If you want a free trial, very simple, just go in and ask for the free trial. If I take this down, come back here and go back to MasterSeries, go to products, very quickly down to standalone products, there you are, Masonry, view product, and in Masonry, now if you select start your free trial, it will get you a free trial of Masonry. There's that overlapping opening type reinforcement yield line I was talking about earlier. Some details. So if you want to even see some of the output from the software, there's a nice document. You can view all the output. Everything we saw on screen is being output to the printer. You can actually download that as a sample as well. So feel free, and here's the power pad limits to play with the software and enjoy. So ladies and gentlemen, so people, thank you very, very much. Goodbye, have a safe day and stay safe.